Picture this. The James Webb Space Telescope, peering deep into the vast cosmos, has made an astounding discovery, unraveling a celestial mystery that has baffled us for ages. For it is in a small patch of the sky that it unveiled about 50,000 objects, the majority being background galaxies influenced by the gravity of the imaged cluster, Abell 2744. The cosmos, you would think, would be teeming with matter and antimatter, but this image tells a different story. It seems all stars and galaxies shown are made of matter. But wait, it gets even more intriguing. The survey also unveiled many gravitationally lensed background galaxies, some of the most distant ever discovered. Now, to understand the significance of this, we have to go back to a time right after the Big Bang, when the universe was a dark, opaque place, as stable, neutral atoms absorbed visible light. The formation of the first stars wasn't an instantaneous event. It took tens to hundreds of millions of years, a process both fascinating and perplexing. And the question remains, how did these early stars and galaxies light up the universe, making it visible? The JWST Uncover survey, in its pursuit of this cosmic challenge, has tracked galaxy evolution across cosmic time, shedding new light, quite literally, on the story of galaxy evolution. It's revealed some of the earliest galaxies ever found, and a very young proto-cluster of galaxies, just 650 million years after the Big Bang. And these background objects appear magnified, stretched, due to gravitational lensing, giving us the deepest views of the universe, transporting us back to a time when star formation was at its peak. However, the discovery that takes the cake, the one that has reshaped our understanding of the universe. You'll find out soon enough. Stay tuned. Hey there, curiosity explorers. Ready for another dive into the unknown? I'm your guide, Caesar, and with me today, as always, we have the brilliant Sonia, ready to unpack and explore the mysteries of the universe with us.
Hello, intrepid explorers. I am thrilled to venture into the unknown with you all once again. Today, we're going to embark on a cosmic journey that will blow your mind.
That's right, Sonia. So don't forget to subscribe to Curiosity Wonderland. Drop a comment, share your thoughts, and share our podcast with others. Your engagement is what keeps us going. Together, let's quench our thirst for knowledge and unravel the incredible mysteries that our universe holds. So let's dive deeper into this cosmic puzzle, folks. This image we're talking about, it shows us the full imaging field of the JWST Uncover Treasury Survey. Now imagine, in a minuscule part of the sky, around 50,000 objects are revealed. Isn't that mind-boggling?
Absolutely it is. So these objects, are they all part of the imaged cluster? Abell 2744?
Great question. In fact, most of them aren't. They're actually background galaxies that are affected by the gravity of the cluster itself. And here's another interesting fact. There are no signs of matter-antimatter annihilation, which indicates that all stars and galaxies shown are made of matter, not antimatter.
That's fascinating. Can you tell us more about the nature of these background galaxies?
Certainly. Many of the background galaxies are gravitationally lensed, making them some of the most distant objects ever discovered. Now let's take a journey back in time. Imagine shortly after the Big Bang. No stars have been formed yet, but the first stable, neutral atoms are starting to emerge. They absorb visible light, making space seemingly opaque. These atoms existed in regions of the universe that were born overdense. These regions grew over time, but their growth was limited by a few factors, such as the initial small magnitudes of the overdensities, the cosmic scale on which the overdensities were found, and the presence of radiation that was still energetic.
So this means that the universe was effectively dark before the formation of the first stars?
Precisely. Until the formation of the first stars, the atoms in these clumps remained neutral. It would require ionizing ultraviolet photons to render them transparent to visible light. Now, let's consider the universe as it forms stars for the first time. As these stars shine and merge, they emit radiation, both electromagnetic and gravitational. However, the conversion of matter into energy also causes an increase in radiation pressure, which fights against gravitation. Intriguing, isn't it?
Incredibly so. The universe is truly a fascinating place.
Let's take a closer look at the star-forming regions in the universe. Surrounding these regions is darkness, as neutral atoms absorb the emitted starlight. Yet, the ultraviolet starlight emitted by these regions works to ionize that matter from the inside out.
So the first stars essentially brought light to the universe?
That's a nice way to put it. Unraveling how early stars and galaxies reionize the universe is one of the biggest challenges in cosmology. One of the missions of the Jwst Uncover Survey is to track galaxy evolution across cosmic time. By doing so, it's shedding new light on the story of galaxy evolution within our universe, and is also helping us determine which types of galaxies and when helped our universe transition from an opaque state to one transparent to light. Now, let's talk about Pandora's cluster, also known as Able 2744. This cluster is a massive collection of galaxy clusters. The galaxies that make up this cluster are easily visually identifiable. The background sources, however, are scattered throughout the universe, with many from the first 1 billion years of cosmic history.
That's fascinating. Are there any notable finds from this cluster?
Absolutely. This field of view is known to contain many of the earliest galaxies ever found, as well as the youngest proto-cluster of galaxies ever discovered to date, which is just 650 million years after the Big Bang. Now, this massive collection of galaxy clusters bends and distorts the surrounding space-time. It's important for us to make a lensing map if we wish to understand how the lensed objects themselves actually are, intrinsically. The light we receive from JWST is a composite of the background sources of light with the foreground cluster sources. After mapping out and subtracting the foreground cluster, we're left with only the background signals, which can be further corrected for gravitational lensing effects.
The universe sounds like an amazing tapestry of light and darkness, matter and empty space, all interwoven in a cosmic dance.
Indeed, it's a cosmic ballet, intricate and stunning, that we are just beginning to understand. Now let's delve a little further into the impact of gravitational lensing. Background objects, due to this phenomenon, appear magnified and stretched. Let's take the deep field region of the good South Field, for instance. Here, we find 18 galaxies forming stars so quickly that the number of stars inside will double in just 10 million years. That's just 0.1% of the lifetime of the universe. Can you believe that?
That's incredible. It's hard to wrap your head around the scale of such processes. Did you know that the term gravitational lensing was coined by physicist Orest Chwolson in 1924, long before we had the technology to observe this phenomenon directly?
That's an amazing fact. It just goes to show how far we've come in understanding the universe. Now, the deepest views of the universe, revealed by space telescopes, take us back into the early history of the universe, where star formation was much greater and where most of the universe's stars hadn't even formed. Many of the most distant galaxies are found in close proximity to other foreground galaxies, whose mass distorts and magnifies the light from background objects. This phenomenon allows us to glimpse galaxies that are too small, faint, and distant to otherwise be seen. It's thanks to surveys like the Jwst Uncover Survey that we've been able to reach these depths. In fact, the Uncover Survey, with lensing enhancements included, reaches the deepest of any Cycle 1 JWST program. The deeply imaged galaxy cluster Able 2744, also known as Pandora's cluster, is a key part of the Uncover Survey area. Yet, it's important to consider that ultra-distant, massive galaxies create too little ultraviolet light to explain cosmic reionization. In fact, the most bright, distant, massive galaxies found in surveys such as these cannot account for the majority of ultraviolet ionizing photons needed to make the universe transparent to light. This reveals just how vast and wondrous our universe is.
The universe truly is full of mysteries, isn't it? Each discovery leads us to a new set of questions, and the quest for answers continues.
Now, although they are bright and powerful, ultra-distant massive galaxies and quasars only account for between 5 and 20% of the needed ionizing photons. More than 13 billion years ago, during the era of reionization, the universe was a very different place. The gas between galaxies was largely opaque to energetic light, making it difficult to observe young galaxies. That's where the James Webb Space Telescope comes in. peering deep into space to gather more information about objects that existed during this era.
So, despite their brightness, these massive galaxies and quasars can't account for all the ionizing photons needed to make the universe transparent to light?
That's correct. Despite some hopes, neither the quasar emissions can fill in that gap. However, gravitational lensing recently revealed 8 tiny, faint, distant dwarf galaxies. These galaxies would normally be invisible to even Jwst at these great distances, but thanks to gravitational lensing's severe brightness enhancement, an effect of Einstein's general relativity, we can catch a glimpse of them.
Wow, that's incredible. How many stars do these dwarf galaxies have?
These dwarf galaxies have only about 1 million stars each. Interestingly, they're about 100 times as common as their bigger, brighter counterparts. Even at early times and great distances, the properties of these faint, low-mass galaxies appear very similar to the same mass galaxies we see today.
And what role do these dwarf galaxies play in the reionization of the universe?
That's a great question. These small galaxies have been caught producing 4 times as many ionizing photons as previously assumed. So their role in cosmic reionization is significant and may well rewrite our understanding of this major transition in the history of the universe. Now, while young stars produce ionizing photons that freely travel throughout the universe, early galaxies had their light absorbed by the intergalactic medium, which was filled with neutral atoms. Only a tiny fraction of light from these galaxies escapes. However, given the vast numbers of dwarf galaxies, even a small fraction of ionizing photons can be primarily responsible for reionizing the universe.
So it's these little cosmic dwarfs that are doing the heavy lifting, not the quasars or bright galaxies?
Exactly. For the first 550 million years of the universe, neutral light-blocking atoms persisted in the space between galaxies, continuing what's known as the cosmic dark ages. Once the last of that neutral matter becomes reionized, starlight can propagate freely through the universe, marking the end of the reionization epoch. So even though they may be tiny, these dwarf galaxies have played a monumental role in shaping the universe as we know it.
That's a humbling thought. It just goes to show that even the smallest entities can have a massive impact.
So to sum it all up, the James Webb Space Telescope has shed light on a cosmic mystery. The tiniest galaxies were responsible for making the cosmos visible. In the vast universe, it's the smallest, most distant galaxies that were discovered to produce 4 times as many ionizing photons as we previously thought. This discovery completely flips our understanding, confirming that it's not the quasars or big bright galaxies, but these tiny cosmic dwarfs that primarily reionize the universe. In other words, the universe cleared its own cosmic fog, thanks to the might of the small.
It's such a profound realization, isn't it? These tiny galaxies, barely visible to even the most advanced telescope, played a monumental role in shaping the universe as we know it. So the next time you feel small or insignificant, remember the role of the dwarf galaxies in lighting up the universe. On that note, we want to thank you all for joining us on this journey through the cosmos. If you enjoyed our exploration today, go ahead and blast that like button.
Yes, please do. And don't forget to share this episode with your friends and comment your thoughts below. We always appreciate hearing from all of you. Until next time, keep looking up.
Yes, keep exploring and asking questions, and remember, even the smallest entities can have a massive impact. Signing off for now, thank you, and goodbye.
Goodbye, everyone. Stay curious. This fascinating information came from the article titled "JWST Confirms the Tiniest Galaxies Made the Cosmos Visible," penned by Ethan Siegel and published on March 4th, 2024, on the Big Think website. If you wish to dive deeper into this topic, you'll find the full URL in the video description. Now I must be off.